And now we are going to calculate the equilibrium conversion. The reversible gas phase decomposition of nitrogen tetroxide N2O4 to nitrogen dioxide NO2 is given by N2O4 goes to 2 of NO2, and in the back direction 2 of NO2 goes to 1 of N2O4. This reaction is to be carried out at constant temperature. The feed consists of pure N2O4 at 340 K and 202.6 kilopascals, which are 2 atmospheres. The concentration equilibrium constant Kc at 340 K is 0.1 moles per liter. A. Calculate the equilibrium conversion of N2O4 in a constant volume gas reactor. And B. Calculate the equilibrium conversion of N2O4 in a flow reactor. So, here we have the reaction. N2O4 goes to 2 of NO2, and 2 of NO2 go back to 1 of N2O4. So schematically, we can put A goes to 2B and 2B returns to A. They are at equilibrium. And at equilibrium, the concentration of the reactant species are related by the relationships dictated by thermodynamics. In thermodynamics, the constant Kc is equal to the concentration of the products elevated to the stoichiometric coefficient, divided by the concentration of the reactants elevated to the stoichiometric coefficient. So Kc is going to be the concentration of B elevated to the second power, because the coefficient of NO2 is equal to, divided by the concentration of A at equilibrium elevated to the first power, because the stoichiometric coefficient of A is 1. So here we have the stoichiometric table, in which we have the species N2O4 and NO2, the symbols A and B. Initially of A, we have Na0. The change is minus Na0 times X, because A is disappearing, that's why it's negative, and remaining is going to be Na0 minus Na0 times X, which is going to be Na equal Na0 times Y minus X. Of B, initially we have 0, the change is 2 Na0 times X, because for each one of A, 2 of B are formed, so NB is going to be 2 Na0 times X. Now, with these expressions, for batch system, we have that the concentration of A is equal to Na divided by the volume B, but the volume is constant, so it's equal to Na divided by the B0, and Na is equal to Na0 times 1 minus X divided by B0. Na0 divided by B0 is Ca0, so we will have Ca0 times 1 minus X. And the concentration of B is going to be 2 Ca0 times X. And the concentration of A initially, we can have it using the ideal gas law, in which the concentration of A0 is equal to Ya0 times P0 divided by RT0, Why is 0 is equal to 1? Because pure N2O4 is going into the reactor. The pressure, total pressure is 2 atmosphere. The gas constant is 0.082 atmosphere liter divided by mole Kelvin, and the temperature 340 K. So we will have that CH0 is equal to 0.7174 moles per liter. At equilibrium, X, the conversion X is equal to Xc, the conversion at equilibrium. So we substitute this equation for Ca at equilibrium and Cb at equilibrium, and we will have that Kc, which is equal to the concentration of B at equilibrium elevated to the second power divided by the concentration of A at equilibrium elevated to the first power. So we have that concentration of B elevated to the square. If the concentration of B is 2CH0 times X, to the square is going to be 4 CH0 squared X E at equilibrium elevated to the second power, divided by Ca, which is CH0 times 1 minus X at equilibrium. So we will have that Kc is equal to 4 CH0 Xe at equilibrium, X at equilibrium to the second power divided by 1 minus X at equilibrium. And from here, X at equilibrium is equal to Kc times 1 minus X E divided by 4 CH0, all of that to the 1/2. And we will resolve this equation by the quadratic formula. And for a batch system, we will have that Xe is going to be 1/8 of minus 1 plus 16 CH0 divided by Kc all to the 1/2 divided by CH0 Kc. And for the flow system, we have that expression in which it comes from the integral tables. So X for the batch is equal to 0.44. And for a flow system, the stoichiometric table is the same as that for batch, except that the number of moles of each species, Nj, is replaced by the molar flow rate of that species, Fj. For constant temperature and pressure, the volumetric flow rate B is equal to B0 times 1 plus epsilon x, and the resulting concentration of species A and B is going to be Ca equal to Fa divided by the volumetric flow rate B, but Fa is equal to Fa0 times 1 minus x divided by B, but B is equal to B0 times 1 plus epsilon x. So at the end, we will have that Ca is equal to Ca0 times 1 minus x divided by 1 plus epsilon x. And this last term, 1 plus epsilon x, is the one that appears as a difference between the batch system and the flow system. And so, for the concentration of B, we will have that it's going to be 2 CH0 times x divided by 1 plus epsilon x. And at equilibrium, x equals xe, and we can substitute equations Ca and Cb at equilibrium to obtain the expression that Kc is equal to Cb at equilibrium elevated to the second power divided by the Ca at equilibrium. So it will be 2Ch0 Xe divided by 1 plus epsilon Xe, all that to the square, divided by Ch0 times 1 minus Xc divided by 1 plus epsilon Xe. So we will have at the end that Xe is equal to Kc times 1 minus Xe plus times 1 plus epsilon Xc divided by 4Ch0, all that to the 1/2. And substituting the values that for N2O4 epsilon equal YH0 times delta, and YX0 is 1 and delta is 2 minus 1. So epsilon is going to be 1. Substituting all these values, we will get that X at equilibrium for a flow system is equal to 0.051, which is bigger than 0.044 for the batch reactor.